ester looks like this. Okay? So these are the starting materials. So you need to be able to generate the starting materials. Okay? Now, the bottom line is this is a classic synthesis question. You can come into the office, which I've encouraged you all to do all term. I'm out here for you. I see some of you, and it's been fun to get to know some of you. But others, I don't know what you do with your time. Certainly don't come see me. So the bottom line is, though, that malonic ester will lead to, in some way, a substituted acetic acid, okay? Generally leads to a substituted acetic acid, which you could go on and do other things with, for sure, right? I can take this carboxylic acid and I can make it into an acyl chloride or an anhydride or an ester or whatever I want, right? But generally they lead to substituted acetic acids, and the substitutions come with two substitutions that you can make to the central carbon here originally. So in essence, a piece comes through to the end through hydrolysis and decarboxylation to lend itself to a substituted acetic acid, where you can get two R groups on there. Okay? So we'll go through B here in a minute. But acetoacetic ester starts here, and what you get in the end is the formation of a substituted acetone, which you can go on and do other things with. This is now a ketone, right? So you could, you can actually take off the methyl group, right? That's one thing you can do. But you could do all things you can do with ketones, which means I can add a Grignard to make an alcohol. I can make an amine. I can make an enamine. All sorts of things, right, that I can do here with this. Okay? So we'll do one of each of these, but this is the general strategy. Now, they come through a general set of steps that are similar to both of them. Okay? The first step is going to be deprotonation. Deprotonation here will always happen on the central carbon between the two carbonyls, as we've been talking about, right? Because that's the most acidic proton in our molecule. So you create now a nucleophile, and you run an SN2 reaction. Remember, this has to be SN2 in nature, which means you're adding RBR, so you can add anything that's methyl primary, secondary to some extent, right? Because it's a soft nucleophile, it generally does run SN2, but generally SN2 means primary or methyl, right? So you're adding these primary nucleophiles here. You can repeat steps 1 and 2 and get a second R group on there, right? So this would where R1 and R2 can come from. Sometimes you only add one R group. Sometimes you can add 2 R groups. It's totally up to the product that you're trying to drive toward. Okay? After you do these steps, you generally run hydrolysis. And then you add some heat. This leads to decarboxylation. And voila, your malonic ester or acetoacetic ester synthesis is done. You can go on to do other things, but this portion is done. You've gotten a substituted acetic acid or a substituted acetone. Okay? So B was like that up through step 3. B was doing exactly this. Okay? So if you were to see this on an exam, generally this comes through as something like this. Okay? This would be your product. This would be through step 3. This is what you'd see. So thinking backwards, you would say, okay, did I generate this through malonic ester or acetoacetic ester? And I take a good look at what I have. I see now acetic acid, right? I see acetic acid. That's the first thing I'm going to pull out, right? That I have acetic acid in there. And I can see my R group that added, right? I only have one R group added here, and that's an ethyl bromide. So I can see already the sort of components that came together for this malonic ester synthesis. I know it's malonic ester because I have a carboxylic acid, specifically a substituted acetic acid. Okay? So I'm able to derive all the steps to get to this molecule. I'd start with what's shown here on your homework, which is this guy. Okay? And the first thing I would do is deprotonate, adding my ethyl bromide. So now I'm at this component here. Okay? I have this at the end of step 2. Okay, so this is 1 and 2 together. on your homework, 1 and 2. Okay? The next step says I'm going to use H3O plus in heat. So we follow H3O plus, just doing them one at a time. And heat now is going to pull off one of these, right? It's going to go by the wayside because I have a beta-oxo carboxylic acid moiety. So in this case, I'm coming down to this product here. This here is the end of the malonic ester synthesis. And there's one more step that we need in our synthesis here, and that is to add CH3OH and heat, which gives me the ester. Okay? So that was the CH3OH and heat. Does everyone see how this works? All right. How about you try a couple here? While I erase, you're going to sit and try an acetoacetic and a malonic ester, seeing that you can generate the steps that come together to give you that. So,
How did she get the OCH? The step. Oh, just substitute.
Wait, where did she get the OCH Where did she get the alcohol?
It's what you do when you do
Decarboxylation.
esters. Like, remember when she says you use the same base as the other one, otherwise you get like side reactions, right? I think that's what Dr. Dixon, what did you use to get that OCH3?
the OCH3 was the last step, step 4. It was Fischer esterification. I took the acetic acid and I added it. Are you with me?
It's
Yeah.
CH3OH.
Okay.
I got here,
Homework. She gave us that.
got all the way here, and then I was like, "Darn, style."
Anya,
I'm sorry?
it's in the homework she gave us the page. Like to get
Oh.
that, use OCH, use CH3OH and acid.
Thank you. I was like, where did that come from?
Yeah.
So, I don't know him. I don't care. It's fine.
I thought you said that you were asking me.
I can check before, like when I saw my
I'm
stuff.
picking it up Wednesday. That's like the next time. There's 2 others.
Yeah, so this is R1 and R2. Yeah, you got it right.
Okay. So I have the direct products there on the board that you can see, and then I have a what if slot. Okay? So I really want you to what if this, because on your exam is a what if. It's not the direct product, I can guarantee you. Okay? So the what if slot, right, is in essence giving you a next step, probably a single or couple next steps past what would have been the substituted acetone or the substituted acetic acid. Okay? I know to get this to this enamine, I know I needed a ketone, right? Or an aldehyde, a ketone or an aldehyde. So I should be able to backtrack very quickly from this enamine to now the ketone or aldehyde and see it as either malonic ester or acetoacetic ester. It would be acetoacetic ester, right? Because this is a reaction you only do with ketones and aldehydes. Okay? And this guy, you can see we're in the carboxylic acid family, right? So I would backtrack to what I know I can get from malonic ester or acetoacetic, which is a substituted acetic acid, right? So I would backtrack to the OH. I would take off all this and stick on the OH and see this as a substituted acetic acid. So you need to think the next step through. What can she put on an exam to be absolutely crazy? No, it's not crazy, actually. It's actually very simple. And I say that in the nicest way because I know organic chemistry isn't simple. I am not trying to be belittling in any way. Okay? Let's just be clear. But this is what you want to do to sort of think through the problem. Okay? So, once we can backtrack to what we have, we now want to go in and say where each of these came from. So the guy on the left came from acetoacetic ester. So the first thing you'd be asked to do is show the starting material in the box. We're asking that you know what acetoacetic ester looks like. This is some points, right? So acetoacetic ester looks like this. So I start here, starting material. Then there's a little box that says what synthesis do you do, right, to get to that product there, okay? So we're going to start with just the acetoacetic ester synthesis piece, okay? So what do I need to do to get to that? So I come back and I count out my molecule, right? And I see that this is the base here. This is the base here of acetoacetic ester. It's a substituted acetone. So I see one R group here. So this is R1. And I see a second R group here as R2. Okay? And I've got it all sketched out now. Okay? I've found my acetone. I've assigned one of these links off here as R1, and one is R2, and I'm ready to get going. Okay? So in my box, I'm going to put in NaOET. It doesn't matter which one you add first. So we'll go with our ethyl bromide. Okay? Just to track as we go through, I'll put the little molecule we expect here. So this is what we get there. Okay? I only have one more proton I can pull, right? There's only one more proton remaining there. So I can only get one more R group on there. So I do the same thing, just with a different R group this time. So in this case, I want to use an isobutyl group, right? Yes. Okay? An isobutyl group. And at the end of this step, I now have this piece here, okay, with my isobutyl group on there as well. Yes?
Do you use NaOET as a base because you want to see the
That's right. Anytime I have an ester, I'm always using a base that's going to match my OR group. Absolutely. Yes. Uh-huh. And acetoacetic ester and malonic esters generally have those OETs out there. That's the base substitution there. Okay. All right. And then my last steps here are always going to be something like H3OH plus or NaOH, H2O, followed by a little bit of heat. That gets me to the top molecule I have, and you can see that you have one more step that you need to add here. I could have made lots of different things, but in this case I made an enamine. So this is the base, and then after that, in my case step 7, right, I'm adding CH32 NH and H+. This is the other step past the base acetoacetic ester. I could have done lots of things. I could have done LDA low temp with ethyl bromide. I could have done, CH3OH and H+, to give you a hemi, right, ketal in this case. There's lots of things I could have done. Yeah? Is there a chance that it's going to do enolation? There is, but very little, because first of all, you have a very crowded nucleophile there, and they generally aren't going to do that. Someone asked that question here before. It's a good question. Yes, you can force it, but generally it's not going to do that. Yes?
Will this work in like a crazy cyclic, like a cyclohexane or?
You cannot add cyclohexane or cyclohexyl, like something like this.
No, I mean if you see the ester, the 1,3 ketone, if you see that in will you see that in a cyclic?
Yeah, you can do substitutions in there. Yeah. Yeah. Okay. How do we feel about this? There's lots of discussion. Someone want to tell me what the discussion is and ask a question? No? Nobody wants to own up to it? Are we talking about what we did last night? I can tell you what I did last night. No? Yeah?
Alright, so just be curious, so can you use LDA?
Can you use LDA? No, we don't generally use LDA here. This is a really good question. But LDA is sort of overkill here. LDA is trying to pull off something whose pK is 9. You don't need LDA, and you don't even need the inconvenience of potentially doing any exchange out for that OET. So LDA is not something we generally use unless we have to, unless we're pushed to. Okay? Yes?
Is this supposed to be number 5? H2O, H+?
Oh yeah, it doesn't matter. H3O plus, H plus, yeah. I went crazy. I have H3O, H plus. I have lots of acid in there. Okay. Other questions? Yeah.
Can you explain 7 again? Was that to make your enemy?
7 is to make my enemy, is to get to my what if. Okay? So there's lots of other what ifs I can do. You want to think through them. I can add oxygen nucleophiles. I can add primary amines. I could use LDA and start alkylating. There's other things I can do. You want to go to the next what ifs. Yeah.
For number step 5, would it be better if we use base?
Base is irreversible. I see why people want to use base. To be quite honest, though, acid and then that heat is enough to push the whole thing forward. Yeah. Yes?
So what exactly would you be demonstrating to us on an exam to get through this? Would you just show us?
You'd show the end product and you'd say what was used to create this, and you choose either acetoacetic ester or malonic ester. You put that starting material in the box. Then you start filling in the synthetic steps, and that portion is graded, right? The ability to understand what the starting material is and the ability to show the proper synthetic steps. Okay, yes, sorry.
What's the final product? Is it the enemy or is it the thing on the other side?
How did I decide it's acetoacetic? Okay, so my what if I started with an enamine. I can't get to an enamine really directly from a carboxylic acid. So I'm not even, I'm just going to take that out, right? So I'm going to come back one step and I'm going to make this bond here, right? Get rid of this thing and make this bond here, the double bond O. I come back to that and I say, oh, look, it's a substituted acetone. I know exactly what I'm doing now, okay? Okay, so the other one then is a Malonic ester, okay, so you need to start with the right piece here. So here's my Malonic ester, and this is the tricky one. I'm putting the tricky one up here on the board. It's tricky because you're making a ring, right? So you can't actually use, what would that be, cyclopentyl bromide. What you actually do is use a chain that's got, now, a dihalide, okay? So what's actually happening is you displace one side, you add more base, it displaces the other. I will go through this step by step, okay? So the first thing you do is deprotonate. The second thing you do is react with one side, or an SN2. So this is what I'm going to get. I'm going to draw out the product under step 2 here. So I'm going to get this guy at the end of step 2. Okay? That's at the end of step 2. So I've displaced one, and I have now 1, 2, 3, 4 carbons, right? 1, 2, 3, 4 carbons, my BR off dangling there. I add a little bit more base, okay? And I am going to use a board trick here, which you might need to rewrite. But the second mole of base is going to deprotonate right here, right? It's going to deprotonate still between the carbonyls, always between the carbonyls. Between the carbonyls the first time, between the carbonyls the second time. In this case, I have an intramolecular reaction, right? I have an intramolecular reaction. It's going to displace from the other end of my long straight chain. So at the end of step 3, I have come up with this. Okay? Now all I need to do is get rid of those OETs back to carboxylic acids. Always the next step, right, is some sort of hydrolysis followed by heat, right? So at the end of step 4, I have this guy here. It's the end of step 4. And at the end of step 5, I've gotten rid of this piece here because it's a beta carboxy piece. I'm down to this at the end of step 5, directly this. Yes?
You know how we were saying like esters and acyl chlorides don't need active catalysts to
Yes.
how can we do H2?
Okay, so this is not esters. It was in esters. esters, it was anhydrides. Anhydrides and acyl chlorides, right? So the top two in that chart do not need a catalyst for hydrolysis, and that's absolutely true. But when you get below the keto-aldehyde line, which are your esters and your amides, you either need to add base, OH minus, or acid, H plus, when you do your hydrolysis.
So if it wasn't, because like in a random something else, it's not like an anhydride, you just put water.
Water alone will hydrolyze an anhydride, yes. That's like a tongue, I can't even say tongue twister, because that really twisted my tongue. All right. Yes, all right, so how would I get to my what if then? How am I going to get down to my what if? SOCl2, okay, good. SOCl2, and then this is the tricky one. It's tricky. Not a carboxylic acid, but a carboxylate. That's exactly right, a carboxylate. So you'd be adding something like this. 3 carbons, right? 1, 2, butanoate. It's the deprotonated version of butanoic acid. The deprotonated version of butanoic acid. Does everyone see that? Does everyone understand that you need to go above it in the table? There's no direct way to get from a carboxylic acid to an anhydride. So you go above it in our table. The only thing above the anhydride is the acyl chloride. I know I can use thionyl chloride to get to my acyl chloride, and now I know to move from my acyl chloride to the anhydride, all I have to do is add the carboxylate of what needs to be added. Okay? Question? You do not need to add pyridine. There's a jury out there. Pyridine certainly is going to make it go faster. You can use pyridine, absolutely. Okay.
Can you
Yeah.
just start at 4 and go forward real quick?
What?
Can you start at step 4 and go forward real quick? Because I lost you right at that.
So step 4 was the hydrolysis. This was the end of step 4. So it's literally taking these pieces and just making them OHs, because that's what happens. Esters go back to their carboxylic acids. So now we're back there. And then the heat decarboxylates, right? So this is the decarboxylation. This is my alpha beta COOH that's going to be gone out. And now I didn't redraw it because I have it over there. I walked over here and said, there's the end of that step. Yes?
Is this reversible? Like, could you get from an anhydride to the beginning?
No.
No.
You need to be
It would
synthetically
be
moving
synthetic.
forward. Yeah.
Okay.
You could, but you're going to have to push yourself to
Right.
get there. Yeah. Not reversible. Many of these steps aren't. Yes?
Is there a way to tell, like, when you get to your ketone that it came from these methods or equation and then decarboxylation?
Okay. So generally when I see a simple substituted acetone or a simple substituted acetic acid, this is a faster way to go and a more guaranteed way to go because of the irreversibility almost of all these steps. The acid-base step, the SN2, you know what I mean? So there's a lot to say about going through it this way, okay? But no, I am sure that you can take these products and come up with alternative ways to get there. But you will be tested directly on the acetoacetic ester or the malonic ester. There is a section on your test that's requiring that you go through these steps. And if you go a different way, we'll give you some credit, but we won't give you full credit. So, but I totally agree. There are likely other ways you can go. Yes?
Can you explain again how we know whether we start with the malonic ester or acetoacetic ester?
Yep, so simple. Malonic and acetoacetic ester on the right board. You can either be directly the top line, right, which would be a substituted acetone. This is acetone. I circled it here. This is acetone, right? Substituted acetone. I can just see some things off. So I got to hone in on that carbonyl and say, is it an acetone? Is there just a CH3 on one side and a C on the other? Is it acetone? If the answer is yes, then I'm doing acetoacetic ester. If I hone in on that carbonyl and I see a carbon on one side and an OH on the other, I've definitely come from malonic ester, okay? But that requires that you take your next steps and come back once, right? So I've got to be thinking, oh, what do I have? What could I have come from, okay? through to the end. Okay? Yes?
We used a carboxylate because we were going from the acyl chloride, right?
That's right. The only negatively charged nucleophile you use for interconversions in that tree are to go from an acyl chloride to an anhydride. And what is the reason for that? What's the reason that we can use our carboxylate to go from an acyl chloride to an anhydride where we can't use any other negatively charged nucleophile at any other point? Because it won't deprotonate at the alpha site, it won't deprotonate at the alpha site. That's absolutely right. I can't do that with other interconversions. I can't add alkoxides, right? Deprotonated versions of alcohols, because they will deprotonate the alpha site. I cannot add deprotonated amines, right? Like an amide of any variety, NH2-, because they also will deprotonate the alpha site. So the only one I can use are the carboxylates. Yes?
And that's because it's a more stable anion?
The anion itself, you're talking about the carboxylate?
Yeah.
Yeah, it's because it's a weaker base, right? And it's a weaker base because it's generated from a stronger acid. And the reason it's weaker is because it's resonance stabilized. Yes, it all comes back together, right? All folds right back to the Orgo 1 general chemistry knowledge that you have so firmly held in your precious brains that are worth a lot of money after all this education, right? You guys just look so done. Yeah.
So the carboxylic acid one has to come from malonic acid?
Yes.
Okay, and the other one has to come, if it has
Yep.
2 R groups, has to come
Yep.
from.
Okay. All right, let us try problem, 4 was the next one. Okay, so let's try 4. 4, right side, so I guess 4B. Likely 2 answers to this, right?
Yeah, but then we have a lecture on Monday.
Okay, so this was 4B. These were your ketones, and I said go to the alpha sites, right, and add on these ester linkages. Directly, take that carbon directly and add it back, a C double bond O, directly to that alpha site, followed by an OET, right? So this allows me to see that, all right? Everyone see what I did here? Literally to the alpha site, I added the carbonyl of this ester linkage. Yes?
Oh, you missing a carbon in the first one. At the very end.
Oh, missing a carbon. Thank you. Okay, thank you. All right. So now you can break these apart. In this case, this would be your new bond, right? No? Yes? Yes.
Yeah.
And in this case, this guy would be your new bond. It's kind of hard. Let me put a squiggly line instead, because those are like double bonds next to each other. Here we go. So here's your new bond. Here's your new bond. Okay? And you could have chosen either. Did you all choose one over the other?
Yeah.
Let's say, which one did you choose? The bottom one. And why would you choose the bottom one?
Ester.
It's a more stable anion. Good job. I'll give you a point extra credit for doing the bottom one. The top one you'll get full credit for, just not that extra credit. You're absolutely right. Good job. Good thinking. Are there any issues with this? Yeah.
Are there 2 possible new bonds that could have formed?
Are there 2 possible new bonds?
Like in the class example, I think it was the top ketone, like the bond
I
directly
don't,
to the right of
we
it.
can look at it. I don't think so. Jim plays it in this one, but we can figure it out.
Okay.
Okay. Is everyone good with that? All right. So the next question was on 5, right? 5 was coming through to 2 intramolecular reactions, aldols, right? So you would have started from, I haven't unfolded mine. I hope we're okay with that. I'm not about to unfold them right now. But generally, this was your starting material here. It's just not unfolded. I'm not going to bother doing it. This was your starting material. This was your starting material here. To get to the top row would have been a cross between this guy out, Rhea, I think you were the one that asked. Okay, so this A to F cross leads out to this guy after heat, which does the formation of our conjugated system here. The question is, what happens in the last step? The last step is NaOH and H2O, followed by heat. So if I do NaOH and H2O, that's a sign of hydrolysis for me. So I'm going to say, are there any carboxylic acid family members? And there are. There's an ester. So that is going to give me, just at the end of that step, something like this. Okay? Which is negatively charged, right? There's no H plus been added back yet. And then heat is going to do nothing to this molecule. It can't do anything because there's no beta oxo group. Yes?
Okay, can it, because it's NaOH and water, could it not take the H of the water and make...
Okay, that's a good question. How am I going to answer that question? How would I answer that question? Acid-base chemistry. So I'm going to try it. Sure, Ria, we can try. Here we go. So this is what we're at then at the beginning, at the end of that. We get to this, and OH minus, and I find the acid on each side. This guy is 16. This guy is 5. Which way is this going? To the left. Okay? Do you see that? Yes. If you put an OH on there because you assumed acid workup, that's fine. But I'm just saying, the end is negatively charged. Yes?
Why did the the ester move?
Oh, it shouldn't have moved. Sorry about that. Does everyone see I moved it because I'm just working really fast? You all have it in the right place or the wrong place. If it's in the wrong place, move it back. Or just put a note there. Just put a note. I just moved it. Does everyone see that? Wasn't intended for movement. No movement. Is everyone okay with that? All right. Everyone was okay with the bottom line. You were able to decarboxylate. All fine? Okay. So what was left? There was one more question. Back to the back here. Oh. Okay. So the last page is trying to get you back to doing some of the old reactions again. And this old reaction might be new, a new old reaction. So when you take this guy here, which is what you form after the Diels-Alder, and you react this with aluminum trichloride, you actually get this product here. Okay? That's the direct result of that anhydride reacting with aluminum trichloride. And you know, with aluminum trichloride as a catalyst for these reactions with benzene, you know that the next step is to lose the bond on the other side of the atom attached to the aluminum, right? So it would be one of these bonds to come back and satisfy that aluminum. Okay? So this generates an electrophile that looks like this. Okay? And this is indeed what adds to the benzene. So when you add benzene to this, okay? So your next step was to get this guy attached. How do you get that attached? What do I need to make it? Well, I got to make an electrophile. That's right. I need to think about some way. This is not to say there's only 2 steps. I'm just saying some way, like not just one step. Okay. So some way to get to something like this, right? Because that's going to capture it. I do? How am I going to exchange out that piece there? What does that look like? It's got this crazy aluminum on it, but if I take off the aluminum, it looks like a... I just use SOCl2, right? You might have gone and done other things, and they might work. But I'm just saying, simplistically, you can do that. Am I right? Does everyone see that? Okay. Yes? Because it's going to create an acyl chloride, and acyl chloride with aluminum trichloride will give me that same catalyst, right? That's acylation of a benzene ring. Yeah? Yes, you'd use AlCl3 next. Okay? So the fastest way would be SOCl2 followed by AlCl3. Okay? All right. I have one question for you all, because I'm curious as to how you did this. So this is my question to you. On the first page, on the bottom, I'm curious what you all did with this guy. Because I can see my starting material in my product. This is gone, right? So how'd you get rid of that guy that I circled there? Yeah. Iodoform. Good. If you use that, you're using the new material. The new material is tested somewhere on your exam, so I want to make sure that you all know how to get rid of a single methyl group. From a methyl ketone, you can use the iodoform reaction, which is I2 and NaOH followed by H+, and then you would need to get to the aldehyde, so you'd need dibol. Okay? So everyone, you could have done it a different way, for sure, and you're not going to lose points. I saw some of you doing things like going down to the alcohol and then doing it using ozonolysis. Also fine. That's just not the new material. So I'm out here saying, if the iodoform reaction is on your exam as a reaction set of conditions, make sure you know that it takes off a methyl group, right? Make sure you know that. That's important. Yeah. It's probably better on an ester, but we did show it in class. So if you use that, that's fine. We did show it in class like 2 weeks ago, 3 weeks ago. I don't even know. I've lost track of time at this point. Yeah. Iodoform leads you to O-, it leads you to a carboxylate, so you need acid. It's what happens. Go look at the reaction. I already did it. It's in your notes. Yeah?
What if you don't have a methyl ketone? Would that do iodoform?
If you do not have a methyl ketone, it isn't going to do, oh, that's a nice new safety hazard. It isn't going to do anything. You need a methyl ketone in order for it to react. An ethyl ketone, like this guy, will not react. You can certainly do I2 and NaOH, and you'll iodinate all alpha sites, right? But it's not going to drop off the group after that. Yeah?
Could you explain where you would use lithium aluminum hydride and where you would use dibol?
So lithium aluminum hydride always gets you all the way down, right? All the way down to your primary alcohol. Dibol is a stop at an aldehyde, right? Dibol is a stop at an aldehyde, which is what I, want to do here. Yeah?
Is that going to polyhalogenate or just one?
NaOH will polyhalogenate. It'll go ka-doo-ka-doo. It really goes crazy. You like that? All right. All right. Are there other questions about the homework? How did we fare? Did we fare okay? Was the homework fair? I warn you, that homework is looking somewhat like your exam, so you've got to make sure you can get through it. I'm out here, I'm telling you, you've got to work on it, okay? All right, so last time, just have a few more things to say. Last time we were talking about Michael reactions. I just want to remind you about the Michael reaction and talk to you about how do we know it's going to do direct or conjugate addition, okay? So as a reminder, this Michael reaction happens only from alpha beta unsaturated going to test very simplistically of alpha beta unsaturated ketones and aldehydes only, okay? To kind of simplify the material as we come to the end. It's a very interesting unit, and it's extraordinarily interesting to see how the amides do more conjugate addition because their carbonyl center is so much less electrophilic. And it's a beautiful sort of collapse back to the material. But I sometimes think that pushes the envelope a little too far. So we're only going to be talking about the alpha beta unsaturated ketones or aldehydes. We said there's 2 electrophilic sites, right? Here's one electrophilic site, the one we've always been working with, right? This one is actually referred to as a hard electrophilic site. And this guy is another electrophilic site, which we see from resonance. And this electrophilic site is what we would consider a soft electrophilic site. Okay? Hard and soft is generally about the concentration of charge. This center, the carbonyl center, is a very concentrated positive charge. This out here is a little bit more diffuse because of the resonance effect. It's a little less sort of it's not a centralized charge, but a little fluffier. And so there's this general concept of hard, soft interactions. And surprisingly, it follows along with what you know about conjugate bases. Very strong conjugate bases are in essence referred to as hard. They are hard because they have concentrated, localized charge in their areas. And as you come down to the moderate nucleophiles and even further on down to the weak nucleophiles, those are considered soft. Soft because they don't have as centralized a charge around their nucleophilic centers. Okay? So whether or not you're going to attack for what we would say is direct addition as we said last time is what we call 1-2 addition. Remember, we number our systems here as 1, 2, 3, 4. 1 being the oxygen always and numbering through the double bond. 2 is the site of attack, that carbonyl carbon, that's our electrophilic site. Things that do direct addition to ketones and aldehydes are reducing reagents, our Grignards, and organolithiums. Those generally will do that. What else do we have? Okay, something else might come to me here in just a minute. What we do here is what we know as conjugate addition. And conjugate addition is also known as 1,4 addition, where the electrophile adds to site 4. Okay? There's a whole slew of things that do conjugate addition because they're moderate to weak nucleophiles. So things that do this are lots of neutral amines do this. NaCN does this. This is the only time you see a Gilman do this. It's not swapping out for a Cl, which is what a Gilman usually does. A Gilman will add to the 4th site. It'll add that R group to the 4th site. That one's pretty incredible. I always find that one pretty amazing. So these are the types of things. Now, if you look into these 2 lists, the list for direct addition are all strong bases, centralized, localized charge. And the things that are doing conjugate addition are all your weaker varieties. So let's just take one example of each and show this reaction so you can get this. So this is really going back to your acid-base chemistry, making sure that you know, right, your acid-base chemistry. So I choose something like this, and I do an organolithium. My organolithiums go in right for the carbonyl. Okay? Hard. And what I get out of that is this product here, which obviously needs some acid workup in order to get to my alcohol product. Okay? Direct addition. Organolithiums, concentrated charge, really strong nucleophiles right at that. Okay? Conjugate addition is something like CN. CN minus is going to do something like this. Generally, I actually run this in HCN. So as a direct result, you get this product, and this product picks up from the acid And in the end, you have your conjugate addition product. Remember, we called our conjugate addition product our thermodynamic product, and our direct addition product our kinetic product. Someone tell me 2 things I can do to this molecule here to react with Cn minus. Got a product there? I want to know 2 things I can do to react to Cn minus. What are some things I can do to make it into something else? Hydrolysis. Hydrolysis is going to make that a carboxylic acid. Absolutely. This is my product. This was the Cn right here. This was the carbon of the Cn. Hydrolysis. One thing I can do. Don't forget, cyano groups can be hydrolyzed. What's another thing I can do?
Can you reduce it?
I can reduce it using
NaNH2?
not NaNH2.
NH2, NH.
What am I going to use to reduce my nitrile? Lithium, aluminum hydride. Now that's going to have subsequent reaction out here, right, to get to a primary alcohol. Is there some way I can prevent that from happening? A protecting group. Okay? These are 2 classic reactions with nitriles. Okay? Not to be forgotten. And that's all I have to say today. So we'll be in here on Wednesday, reviewing for the exam, clicking, etc. Break.